and then let's see if we can start.
If this works at all. Okay. All right. Cool. There we go. Right. So, as Lars said, I'll be talking about guided Kleene Algebra test, which is a way to do verification of uninterpreted programs in nearly linear time. This is joint work with Stefan Smolka, Nate Foster, Justin, Sue, Dexter Cozen, and Alexandra Silva. And let's just get right into it with an example. So suppose one day you're programming and you encounter some old code that you wrote, and it looks like this. And you stare at it for a while, and you frown because it's not the nicest code. And then you stare at it some more. And eventually you realize that it seems like this code can actually be refactored like this. And then you wonder, can I prove whether these two programs are equivalent? And moreover, can I check this mechanically? And more precisely, can I check this for any realization of the variables for the predicates in the code that we put in there? So this question has been raised before. It's been studied extensively in the framework of Kleene Algebra with tests, which you may be familiar with, for instance, if you attended the tutorial on Monday. It's been studied for this large class of programs that's built from non-deterministic choice and non-deterministic iteration. It turns out that deciding equivalence of programs that are built like this is piece-based hard. There is a quasi-equational axiomatization of equivalence, and the automata model that corresponds to it is called automaton guarded strings. And Dexter and a number of collaborators worked this out over the years before. And there's also a large body of work that goes into uninterpreted programs. These are just a few references. And what we've done is we looked at a fragment of these programs, so it's not entirely obvious, but part of the programs that you can build with CAD are more traditional programs built with if, then, else, and while, do loops. And it turns out that deciding equivalence of programs like that is nearly linear. That is a technical term. And we have a quasi-equational axiomatization for equivalence of them with a little caveat that I'll get into. And the automata that correspond to these programs are a fragment of the automaton guarded strings. So just to drive this home, we can decide equivalence in nearly linear time. We have a quasi-equational axiomatization and an automaton model that corresponds to these programs both ways, which is known as a Cleany Theorem. So what do the programs, what are they, the programs that we look at, what are they built from? Well, you have assertions, which have primitive tests. You have disjunction, there's conjunction, there's negation, and you have a false and a true constant. And then you can have assertions. You have primitive programs, sequential composition, if then else, and while loops. So this is a more concise way of representing programs like that. And it's quite convenient. So for instance, the program that we saw on the first slide looks like this. And the more complicated program looks like this. Now, you can give a semantics to these programs. And a very natural way to do this is to just to assign a predicate to every test and to assign a predicate transformer to every primitive program. So this is called an interpretation. So you have your interpretation of tests and programs. And then you can build a function from programs to relations that is parameterized by this interpretation. So for instance, sequential composition is interpreted as relational composition. because every program given an interpretation is assigned a relation in this semantics. So this is a fairly straightforward and I would say intuitive way of giving a semantics to programs like this. The problem, though, is that you have this parameter in the interpretation, and there's, of course, infinitely many interpretations, and it's not entirely obvious how you would check whether two programs are equivalent under any interpretation. So another way you can go is to give it more of a small step model of these programs, which is given in terms of guarded strings. So guarded strings are words in which you have an atom of the Boolean algebra generated by your test, and then a letter, which is a primitive action, and then another atom, letter, atom, etc., until you reach the final atom. And the way you think of this string is sort of like a trace of your program. So your atom symbolizes the state of your machine. Then your machine does an action, P0, and it ends up in state alpha 1, etc., until it terminates in state alpha n. You can compose languages of words like this. Most crucially, if you have a set of guarded strings, you can do guarded composition in which you concatenate, you sort of mush together two guarded strings that match on the final and initial atom. And then using guarded strings, you can give another semantics of programs like this. Here you do this guarded string composition instead of relational composition. And the nice thing about this is that now we have a semantics, it turns out, we have a semantics of these programs which coincides if and only if they are relationally equivalent under any interpretation. So at this point, we have done away with the assignment of predicates and predicate transformers to the primitives of our program. And because this is a language interpretation, there's a large body of work that we can use to compare languages, which allows us to decide whether two programs are equivalent under any interpretation. So the way you do that is you translate your expressions to automata, and then you check whether those automata are bisimilar. And this procedure is nearly linear in the size of your automata. This is standard work due to Hopcroft and Karp, and Tarjan later analyzed that. So we have decidability. Moving on. So I just talked about how you compare the semantics of these programs, but you can also reason about them syntactically, because they are, of course, expressions. So laws that they turn out to satisfy are, for instance, the one on the left here, where if you have an if-then-else branch, where the content of the branches is the same, then that's the same as just executing the content of the program, because apparently the predicate does not matter. And for instance, here you can switch around the branches of if-then-else if you negate the condition, which is something I'm sure you've all done at one point. And now you can use laws like this to prove equivalences with programs. So for instance, this one with the if-then-else, you encode like that, and then you successively apply axioms to arrive at this program. For while loops, it is tempting to give an inference rule like this, so to regard them as a fixed point. So if the program E is the same, if I can prove that it's the same as if when A is true, I execute F, and then I continue with E. And if it's not true, I execute G. Then it's tempting to conclude that E is actually an A loop on F followed by G. There's one problem with this, and that it's not sound. So you can prove nonsense with it. So you need to be a bit more nuanced. So the nonsense that you can prove is that this program, which doesn't terminate, is equivalent to this program, which does terminate. And that's, of course, something that you don't want. So you need to be a bit more nuanced and say that you can only do this on loops that are productive. What exactly that means I'll refer you to the paper, but this is an idea that goes back to Saloma in the 60s. Then there's some other axioms about loops, and this side condition on loops is actually not very important because it turns out that you can make any loop body productive. And now you can prove things about loops like this. So when the loop terminates, then the loop condition is false. With the axioms that we've seen so far, so these axioms actually relate to the semantics. They are sound. So provably equivalent programs are semantically equivalent. And a natural thing to ask is whether you can prove the converse. So the way you do that is what you need to do is you need to be able to take an automaton, turn that back into an expression in such a way that the automaton for an expression is equivalent to the expression that you started out with. Moreover, if you take bisimilar automata, you should get equivalent expressions. When you have this, you can prove completeness of the axioms like this. I won't go into the details. So that's the axiomatization part. So I briefly mentioned before that we needed to turn expressions into automata, and here we've seen that we need to turn automata into expressions. So this idea is called the Cleany Theorem, back to Cleany's classical theorem about automata and regular expressions. So by now I hope to have convinced you that this Cleany Theorem is really the powerhouse of our results. So just some words on how this Cleany Theorem works. We have this automata model in which you have transitions labeled by atoms and actions, and also outgoing transitions. So I have an automaton like this. I start in this state, and now I can read an atom beta and perform the action P to arrive in S2. And then I can read gamma and perform Q to go back to S1. And now I can terminate reading alpha. And this is a way of accepting this guarded string by this state. It's a coalgebra of this type if you're into coalgebra. So the way we turn these expressions into automata is we follow a construction due to Thomson, but we adapt it to our automata. So you basically turn the parts of your expression into automata, and then you glue them together. For instance, like we do for if then else here. We take the if branch, we take the else branch, and we glue them together according to the predicate that guards the if, like this. We can do the same for sequential composition and for loops. And this gives us a way to go from expressions to automata. Vice versa is not that easy, because it turns out that there are automata that you cannot convert back into expressions, such as this one. But we have a side condition which structurally restricts the automata in such a way that you can turn parts of the automaton into expressions, essentially eliminating states as you go until you have just one state, which is linked to the expression that you want to obtain. So this gives us the Cleany Theorem. And these so the conversion from automaton, I should say from expression to automaton, is constructive, as is the other way around. And the automaton that you obtain from an expression is linear in the size of the expression that you start out with, which is crucial for the decision procedure. The side conditions that we needed for completeness about bisimilarity versus equivalence and doing the round trip from expression to automaton back again also turn out to hold. So this gives us the Cleany Theorem. In terms of future work, what we would like to do is we would like to expand more on the coalgebraic perspective of this. I briefly mentioned that the automata are coalgebras. And we want to have a co-equational description of the automata that we looked at. So the structural restriction that allowed the conversion back into expressions. We want to be able to instantiate this, so to add extra constraints on how the Laffers behave. And we want to do away with the side condition about productivity, but in a nicely algebraic way, which we think is possible. Yeah, that's it. So we'd like to dedicate this work to Laurie Handren, who passed away last year, but whose papers inspired us to find the right condition on automata. If you're interested in the slides, I'll put them online, and the paper with all of the nitty-gritty algebraic details can be found on arXiv.
Thank you so much. Do we have some questions? And there's a question here from Slido which says, what is a co-equation? Do you want to explain that?
So we're in the process of understanding that completely, but the way I understand it now is that it tells you what patterns to avoid in the coalgebra. So what kind of succession of transitions or patterns of transitions that you don't want to have. And we think that this can help us avoid automata like this.
Okay. Other questions? So I have one. I was curious about whether you could tell us a little bit about. So now you have this fragment that you've considered here in this work. So what's the killer app, if I may phrase it like this, for this fragment? I mean, what kind of applications do you have in mind where this fragment would be suitable?
It is mostly of theoretical value, which to me could also be an application.
Sure.
So one thing that I should be careful with this because I'm on record, but I secretly hope that this fragment turns out to be what is called a covariety, if it's characterized by co-equations, and that means that while programs would actually be coalgebras for a comonad, which I think would be really cool, but it's not exactly applied.
Okay, fair enough. Any other questions? No? All right, thank you very much then.